In this presentation, we're going to look at sorting and searching, and we'll start off with a sort algorithm they call selection sort. And the idea is, if we have a unsorted list of values and we have two indices, one starting at the beginning of the list and the other starts at the next one and runs all the way down, the second one is going to loop through the rest of the list and try to find the smallest thing. And when it does, we'll exchange it. Then we'll go to the second position, and that's our first index. And our second index, then we'll go to the third position and start there and run to the end of the list looking for the smallest thing. And when we find it, we'll swap it. And we'll continue this process until we get to the last two, and if they need to be swapped, we'll do that as well. So let's take a look at how we might write this. I've got a blank C++ file here. I'll need to include stream namespace standard vector, and that's probably a good start. And again, we can any values that can be compared, you can sort them. You can sort names, you can sort all kinds of numbers. In this case, we'll just keep it simple and sort a list of integers. So we've got a list of random values that we can sort. Might want to write a simple display function. And as you recall, for efficiency reasons, we pass in the vector of integer as a constant reference. So we pass it in. The reason we pass it in by reference is so we don't make a copy of the list every time we pass it in. And since the display function doesn't intend to change the list, we make it a constant reference. So if this builds and runs okay, you see we've got a list of 10 random values. And we might get duplicates, so that's okay. That sometimes happens. So let's see how we might write a selection sort. So we need two, for the selection sort, we have two indices or pointers into the list. One is the location where we're looking for the smallest, where we want to put the smallest thing. The other goes from the second location to the end of the list, searching for the smallest thing. So it's kind of a search swap if necessary type strategy. So we'll call this selection sort, and here we're going to pass the list in by reference because we want to change it, but not as a constant because we want to change. We might want to change it. We will keep track of two indices into the loop, and we can just use I and j. Now notice that we had the I loop go from 0 to less than size minus 1. The reason for that is the last step in the outer loop of the selection sort, we want to stop not at the end of the list, but the one before the end of the list, so that the other loop can search the rest of the list, which in this case is just one thing. So now we want a variable for the smallest index, and I'll set that to -1, meaning that we're assuming we're not going to find it. And I'm going to have another loop. You need to be careful about this copy paste. You don't just blindly do it. You have to make sure you change everything. So I'm going to have another loop j that's going to search for that smallest index. And it is going to start at, the j loop starts at one position beyond wherever I is. So if I is here, j starts here. If I is here, j starts here. So j always starts at I plus 1. And it does go all the way to the last thing in the list every time. It starts at I plus 1 and goes all the way to the last thing in the list. And at each step, this is very similar to our linear search. It really is exactly like our linear search. We're just searching a portion of the list rather than the entire list. So we're going to ask the question, if the value at So we're looking for the value that's the smallest value in here, and it's not just the smallest value in here, it has to be smaller than the value at I, at list sub I. So instead of initializing the smallest value to int max, we can initialize it to list sub I. That's currently the smallest value that's at that location. If list sub j is less than the smallest value, then we found something that's smaller than what's at list sub I, and I want to set the smallest index equal to j, and I want to set the new smallest value equal to list sub j. And I want to keep track of this because I might find something smaller later on. When we're done with this inner for loop, if the smallest index is greater than or equal to 0, I guess it'll never be 0 because j will start at I plus 1, the smallest value of j will be 1, but if it's not negative, that indicates that we found a value that's smaller than what's at list sub j. And if that's the case, then we want to exchange it. So we want to swap the values at list sub I and list sub smallest index. So I starts out at I starts out at 0. Smallest index is assumed to be initialized negative, which means we're assuming it's not found. Smallest value is initialized to the value at list sub I. And j is going to run from I plus 1 or 1 to the end of the list. At each step, we look for something smaller than the current smallest value. And if we find something, we store that index, j, and we store that new smallest value, list sub j. And we keep looking for something that might be even smaller. At the end of that inner loop, when we've run j from the second thing all the way down to the end of the list, if we have found something that is smaller, it will no longer be negative, and so we can swap those two. This works okay, we should see the unsorted list as we saw before, and then now a sorted list where all the items are in ascending order. Interestingly, we could modify the algorithm fairly easily to put the list in descending order if we wanted to. And the change that we would have to make in here is that instead of doing a search for the smallest index and the smallest value, we'd have to do a search for the largest index and the largest value. And it would be a good thing to change the variable names from smallest to largest, but logically all we really have to do is change this from less than to greater than. I'll let you try that out if you like. So the next thing we want to look at is something we call a binary search. And a binary search is done on a list that's been sorted. So the idea of a binary search is we have 3 indices or pointers into the list. One that's at the beginning of the list, one that's at the end of the list, and one that is roughly halfway between the other two. And because the list is sorted, we're going to play a high-low guessing game. We're going to check the value that we're searching for with the value at the middle and ask, is that what we're looking for? And if it's not, we want to know if it's either in the lower half or the upper half. In this case, 34 is greater than 19, so we know it's going to be in the upper half. So we're going to move the lower index to middle plus 1, or middle, and then recalculate middle as being roughly halfway in between lower and upper. And then we re-ask the question, is 34 at the middle? And in this case, it is, yes, it is, so we're done. But if it were not, then we'd ask if it were less than or greater than, and then we get a smaller list. So you can see we're dividing the list in half every time. Kind of a high-low guessing game, a divide and conquer type strategy. And the reason we can do that is because the list is sorted. So we know if it's greater than a particular value, it has to be on the right side. If it's less than a particular value, it has to be on the left side. And because we're dividing this list roughly in half each time, the complexity of the algorithm, or the size of the list, gets reduced by log base 2 the complexity ends up being log base 2 of the number of things in the list, or just log n. The interesting question occurs: when do we stop this loop? When does it stop? It turns out that if you keep searching for a value that's not found, eventually the lower index will become greater than the upper index. So when these two, the lower and upper, they get closer and closer to each other, when they pass each other and lower is no longer less than upper, then that's when we stop. So let's implement this. Let's see if we can implement this binary search. And in this case, I'm going to return an integer which tells us where the value is. And again, we're going to pass in the list by reference as a constant because the search routine doesn't change the list. And we're also going to pass in a target value that we're looking for. I'm going to create a variable called foundIndex and assume that the found index is negative, or that means it's not found, it's not in the list. I'll create three variables called low, high, and mid, and these are my lower and upper and middle indices into the list. We'll initialize low to 0, we'll initialize high to list.size -1, the end of the list, and mid will always be equal to the average, low plus high, divided by 2. And we'll ask the question while low is less than or equal to high, so we want to keep iterating, keep dividing and conquering while the lower index is less than or equal to the upper index. And we want to ask the question, maybe the first thing we ask is, did we find it? So if list sub mid equals the target value, then we found it. And so our found index is going to be equal to mid, and we can break out of the loop. We don't have to search anymore. Now this assumes that we're looking for, we're searching for a single value in the list, the first one that we come across. There's a possibility with a list that you may have more than one occurrence of a value in a list, and in some applications you may want to find all of them, and so we'd have to modify this algorithm somewhat. And in this case, we're just going to assume we're going to look for the first thing that we can find and tell us if it's in the list and where it is. So if we didn't find it, we want to ask the question, is the target value in the lower half of the list? So is the target value in the lower half of the list? And if that's the case, then we want to take the high index and set that equal to mid -1. So if it turns out that the target value is less than the value at mid, then we're going to move this upper or high value just to the left of the middle value, and now we'll be considering the lower half, the lower portion of the list. Because we know it wasn't here, or else that if statement would have been true. We know it can't be in the upper part of the list, or else that if statement would not be true. We know it's got to be in this lower half, So we're going to move the upper index to just left of the middle index, and then do a search on this bottom half of the list. Else, if it's not found here, and it's not in the lower half of the list, then it must be in the upper half of the list. So in that case, we want to take the low index and set it equal to mid plus 1. And now it could be that we've modified either low or high, and so we're going to recalculate the middle index for this list. And loop back around, and as long as low is less than high, we'll do this search and either find it or modify the boundaries of the list to either be the lower half or the upper half. So let's see if we can search for a value of the list. I forget. Here's our list. It looks like we have a 8 in our list, so let's maybe search for an 8. So I'm going to ask the question that if result was greater than or equal to 0, and that means we found it. And so I will write out value found at position result. Otherwise, value not found. So we'll search for a value like 8, and if it's found in the list, we will print out a result that's found at a location. If that result is not greater than a 0, which means it has to be negative, then it means it wasn't found. So if we run this for the 8, and recall the list has to be sorted, so we have to call the sort for the list before we can do the binary search, or it won't work properly. And here it says that the list was found at position 2. Now initially in the unsorted list that's not position 2, but after the list is sorted, the 8 is at 0, 1, 2. So it looks like it might be working okay. Let's try this for something at the end of the list. I forgot now. Maybe a 24. Okay, so 24 was found at position 9, and then maybe we could search for a 0. It's always a good idea to test the endpoints when you're testing out these functions. And it says the value was found at position 0, so 0 is at index 0 in the list. And then test for something that's not in the list. We know there's no negative numbers in the list. And so the value was not found. Negative 9 is not in the list. So that's an interesting different search from the linear search that we saw, where as long as we know that the list is sorted, we can do a binary search or take this divide and conquer approach. Now, let me know if you have any questions about this sorting using binary search, binary searching of a list. We're searching of a list using a binary search.